Hello, so we begin with the first major topic in this lecture series, the rudiments of the theory of Fourier series. In this and the next few lectures, we shall prove the most basic convergence result on Fourier series and look at some simple applications and one somewhat non-trivial application which is important in number theory. Okay, so let's begin with trigonometric series and Fourier series. So what is a trigonometric series? So let us start with the arbitrary 2 pi periodic function f from R to R, which at present is quite arbitrary except that it is integrable over say minus pi. For technical reasons, it is important to work with Lebesgue integrals rather than Riemann integrals. So we assume that f is Lebesgue integrable on minus pi. The main objective is to express f as an infinite series of sines and cosines as you see displayed in the slide, equation 1.1. What you see there is an infinite superposition of sines and cosines, the basic periodic functions with period 2 pi. A series of the form 1.1 is called a trigonometric series. Well, the fundamental question now is what is the meaning of the expression 1.1? In what sense does the series converge, and if it converges, does it return you the function f of x? Well, let Sn fx denote the nth partial sum, that is the sum of the first n terms of the right hand side of 1.1. There are several ways of assigning a meaning to the equation 1.1 and let us look at a few of those in the next slide. We say that the series 1.1 converges to f of x pointwise almost everywhere if the partial sums Sn fx converges to f of x. In other words, for every x, Sn fx converges to f of x. It's a usual notion of pointwise convergence of a series of functions. The other one is when the partial sums Sn f converges to f in mean. You may recall, for example, in engineering courses, the RMS, the root mean square of a function. So what is the mean value of a function? The root mean square, the RMS value of a function gx. So let us consider a function gx on minus pi and let us integrate mod gx squared over minus pi. So we are looking at integral minus pi to pi mod gx squared dx raised to the power half and call it the norm of gx. This is L2 norm or the RMS value of gx as the engineers call it. So we say that the sequence of partial sums Sn converges to f if the norm of Snf minus f goes to 0, and the series 1.1 is said to converge in L2 or converges in mean if norm of Sn fx minus fx goes to 0 as n tends to infinity. Now the third mode of convergence is the Cesaro convergence. So what is Cesaro convergence? We take the partial sums S1, S2, S3. Instead of demanding that the sequence of partial sums converges pointwise, what we ask is that the arithmetic means of this sequence 1 upon n of S1 plus S2 plus Sn, the arithmetic means of these sequence of partial sums converges to f of x pointwise. This is called Cesaro convergence or Cesaro summability. So the third mode of convergence is to demand Cesaro summability of the sequence of partial sums to f. However, we shall need some additional hypothesis on f of x to make any of these things work. To establish convergence in any of these modes, we will have to impose some additional hypothesis on f of x beyond the fact that f is in L1 of minus pi pi. So let's move on a little forward. Let's look at an analogy from elementary calculus. Recall from elementary calculus the problem of expressing a function f of x as a Taylor series. So f of x equals a naught plus a1x plus a2x squared plus a3x cubed plus etc., where a naught, a1, a2 are the coefficients of the Taylor expansion. We all know that there is no hope of getting this kind of expansion unless f is sufficiently smooth. So let us give ourselves enough smoothness. So let us introduce C infinity of R, the space of all infinitely differentiable functions on the real line, and we shall assume that the function f of x, which we are trying to represent in the form 1.2, is infinitely differentiable. We know from calculus courses that even if f of x is infinitely differentiable, even if f of x belongs to C infinity of R, it is not true that f will admit a representation of the form 1.2. I'll leave it to you to look for an example. So we must give ourselves more hypotheses. We must put more restrictions on f of x in order for 1.2 to hold. And there is a certain distinguished subclass of C infinity functions for which the representation 1.2 holds. And for that distinguished subclass, the series 1.2 will converge on some open interval minus r comma r. Okay, so now suppose we have the series representation 1.2. Suppose the function f of x admits a power series representation as in 1.2. How do we get the coefficients a0, a1, a2? We differentiate 1.2 n times and put x equal to 0, and we get the equation 1.3, namely an equal to 1 upon n factorial nth derivative of f evaluated at 0. So the coefficients an can be recovered from f of x via 1.3. Now the question is, what is the analog of 1.3 in the context of trigonometric series? Let's go back to the first slide 1.1 and stare at this equation 1.1. How do we obtain a0, an and bn from 1.1? Let us, for simplicity, assume that the series on the right hand side converges uniformly on minus pi pi. Let's assume that the series converges uniformly. So recall that when a series converges uniformly, the sequence of partial sums which are continuous converge uniformly to f of x, and hence the sum function must be continuous. Next thing is, when a series converges uniformly, term by term integration is permissible. So let us integrate both sides of 1.1 with respect to x from minus pi to pi. What happens? On the left hand side you will get integral fx dx from minus pi pi. On the right hand side what happens? You simply compute the term by term integrals. Integral of cos nx and sin nx over minus pi to pi becomes 0. So the only term that survives is integral a0 dx from minus pi to pi, which is 2 pi a0. So divide by 2 pi, and what do you get? a0 equal to 1 upon 2 pi integral minus pi to pi fx dx. So that's what we have obtained. We have obtained the formula 1.4 for the coefficient a0 appearing in the series 1.1. Again, look at the series 1.1. F of x equal to a0 plus summation n from 1 to infinity an cos nx plus bn sin nx. Multiply by cos kx and then perform the integration from minus pi to pi. Again, term by term integration is valid because we assume uniform convergence, and we are going to get integral minus pi to pi fx cos kx dx from the left hand side. From the right hand side, what's going to happen? Only one term will survive, namely the AK term, the AK cos squared kx. When you integrate from minus pi to pi, you're going to get a non-zero value. All other terms will be 0. So you immediately get AK equals 1 upon pi integral minus pi to pi fx cos kx dx. Likewise, if you multiply the series by sine kx and play the same game all over again, you will get bk equals 1 upon pi integral minus pi to pi fx sine kx dx. So that's equation 1.5 that you see on the slide. So equations 1.4, 1.5 give you the formula for computing the coefficients in the series 1.1, but in deriving these formulas, we have assumed that the series converges uniformly. Okay. Now, these coefficients A0, AK and BK can be computed even if the function is only assumed to be integrable. It is not necessary for functions f of x to be continuous in order for the integrals in 1.4 and 1.5 to make sense. So let us now assume that the function is integrable, and let's make definition 1. Suppose f of x is integrable on minus pi pi. We say that the trigonometric series 1.1 is a Fourier series if the coefficients a0, an and bn are given by 1.4, 1.5. So now we have the definition of a Fourier series. The important comment that I like to make is not all trigonometric series are Fourier series. Note that the series 1.1 is not sufficiently well behaved as regards convergence. Then the validity of 1.4, 1.5 is suspect. Our entire derivation is suspicious. In fact, even if the series 1.1 converges everywhere to a sum function f of x, the coefficients may not be given by 1.4, 1.5. A classic example of this was given in 1906 by Fato. Fato's example is given in 1.6. f of x equal to summation n from 2 to infinity sine nx by log n. The series actually converges for all values of x from minus pi to pi or 0 to 2 pi. The terms are 2 pi periodic. You can work with any interval of length 2 pi. So in this slide, the interval has been taken to be 0 to 2 pi, but that's perfectly fine because everything is 2 pi periodic. The series that is displayed in 1.6 converges for all values of x. Moreover, the convergence is even uniform on a subinterval delta comma 2 pi minus delta for every delta bigger than 0. So we are in a very good situation of uniform convergence on these subintervals delta comma 2 pi minus delta and pointwise convergence everywhere. Nevertheless, the sum function fx that you see in this slide is not going to be integrable, and the coefficients in this series are not the Fourier coefficients of f. In fact, in 1875, Paul Dubois-Raymond established that if a trigonometric series converges to a Riemann integrable function, then that trigonometric series is actually a Fourier series. In 1912, the result was extended to Lebesgue integrable functions. We are not in a position to prove all these claims in this course, so I shall give you a reference to this, namely the book of Bachmann and Naricki. On page 219-220, you see the proofs of some of these claims that I have made. But the main point to remember is that not all trigonometric series are necessarily Fourier series. From now on, we shall only work with Fourier series of f of x. and we are going to assume that the function f of x is Lebesgue integrable on minus pi, and the coefficients a0, an and bn are given by those integral formulae 1.4, 1.5. And we want to prove that under suitable conditions, the Fourier series converges to the original function f of x. The proof is somewhat lengthy and we require a certain number of preparations. The first preparatory lemma is on the slide now, lemma 2. Lemma 2 is an elementary exercise in trigonometry. It says 1 plus 2 cos theta plus 2 cos 2 theta plus dot 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 plus 2 cos n theta is given by the ratio sine of n theta plus theta by 2 divided by sine theta by 2. The first exercise for you in this course is to prove this lemma. How do you prove the lemma? Call the sum on the left hand side of 1.7 as s. Multiply by sine theta by 2. So, s sine theta by 2. That is going to be sine theta by 2 plus 2 cos theta sine theta by 2 plus 2 cos 2 theta sine theta by 2, etc. Now, use the formula 2 sine a cos b is sine of a plus b plus sine of a minus b. Use this formula and you will get the result 1.7. It's an elementary exercise that I am leaving it to you. Okay, so now let us look at the equation 1.8. The nth partial sum of the series is given by a0 plus summation j from 1 to n aj cos jx plus bj sin jx. It's a finite sum, and what we wish to do is to rewrite the finite sum as an integral expression. How do we do that? Go back to the definition of a0, aj and bj. Let's recall, a0 is what? 1 upon 2 pi integral minus pi to pi fx dx. Let's go back to 1.4, 1.5. Here are the formulae displayed. a0 is given by 1 upon 2 pi integral minus pi to pi fx dx. ak is 1 upon pi integral minus pi to pi fx cos kx dx. bk is 1 upon pi integral minus pi to pi fx sin kx dx. So, use these formula over here in 1.8. Substitute those integral expressions for a0, aj and bj in equation 1.8. So, what do we get? We will get the integral from minus pi to pi, and we will have a 1 upon 2 pi factor outside, and a0 will be integral fx dx. aj is an integral of f of t cos jt dt. bj is integral f of t sin jt with a 1 upon pi factor thrown in front of it. All right. So, what do we get? We will get 1 upon 2 pi into integral from minus pi to pi f of t into from a0, that's simply 1 times f of t. aj will be what? F of t into cos jt, and we also have a cos jx. bj is what? F of t into sin jt, and there is a sin jx. So, we have in the integral cos jt cos jx plus sin jt sin jx, that is cos of x minus t j. That is exactly what you see over here. With these integral formulas, Sn fx takes the form 1 upon 2 pi times minus pi to pi f of t into 1 plus 2 cos x minus t plus 2 cos 2 times x minus t plus etc. plus 2 cos n times x minus t dx. Where does these 2 come from? Remember that in a0 the integral was 1 upon 2 pi times integral minus pi to pi, and for aj's and bj's the factor was 1 upon pi. So that's how the 2 comes in. So by using the lemma 1 plus 2 cos x minus t plus 2 cos twice x minus t plus etc. This expression in the parenthesis has been written as dn of x minus t. What is dn theta? Dn theta is 1 plus 2 cos theta plus 2 cos 2 theta plus dot 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 plus 2 cos n theta, which you see as formula 1.10. So that's the dn theta. So we have Sn fx equal to minus pi to pi f of t into dn of x minus t. Now since dn and f are both 2 pi periodic, an integral f of t dn of x minus t dt can also be written as integral from minus pi to pi f of x minus t dn t dt. Okay. So here is a little exercise. Prove that the last two displayed integrals in 1.9 are equal. That's an easy exercise. And the second exercise is prove that the integral of dn t dt is 1. How do we prove 1.11? What is the formula for dn t? Dn t is 1 plus 2 cos t plus 2 cos 2t plus dot 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 plus 2 cos nt. Let us integrate from minus pi to pi and you straight away get 1.11. Alright. Now what do we do with 1.11? We multiply 1.11 by f of x and take the f of x inside the integral. X and t are independent, right? So from 1.11 we will get f of x equals integral minus pi to pi f of x dnt dt. And the other equation is 1.9. So 1.9 gives you an expression for Sn fx and 1.11 gives you fx equals integral minus pi to pi fx dnt dt. We must now subtract, and what do we get? Sn fx minus f of x will be minus pi to pi f of x minus t minus f of x into dnt dt. Alright. So now we have come to this equation 1.12. The idea is to now allow the n to go to infinity and examine whether the integral appearing in 1.12 goes to 0. This is a bit tricky and we must be patient and go slow with this. So let us examine the integrand 1.12. You see the dnt. What is dnt? dnt is the expression that was given earlier, 1.10, right? So sine of n plus half theta. Let us use the addition formula for sine. Sine of n plus half theta is sine n theta cos theta by 2 plus cos n theta sin theta by 2. In the second expression, the sin theta by 2 cancels out. Alright. So what do we get? We will be left with dn theta equal to 1 upon 2 pi cos n theta plus sin n theta into cot theta by 2. So we got two terms you notice in dn theta, a pure cos n theta term and a sin n theta into cot theta by 2 term. Alright. So likewise the integral 1.12 will split it into two integrals. First one will be, there's a 1 upon 2 pi factor which is outside, let's not worry about that, that's innocent. The cos nt into f of x minus t minus fx. That expression f of x minus t minus fx, let us abbreviate it as delta xt for simplicity, right? So 1.12, the integral in 1.12 splits into two integrals as displayed in 1.13 using the expression for dn theta in the middle of the slide. This integrals in 1.13 have to be examined carefully. What happens as n tends to infinity? This is what we shall now proceed to do in the next half hour. Okay?